Hello, my name is Evan Cleveland, and this is Physics 2 Lab 4, the Circuit Lab. So essentially the goal here is we are going to make some predictions and measurements about the behavior of circuits set up with different arrangements of resistors and capacitors. Big physics principles are conservation of energy and charge, the loop and node rules, and then just general behavior of resistors and capacitors in series versus parallel. Some results. The actual values that we measured reasonably matched what we would predict, and then current in an RC circuit is exponentially time dependent. For part 1, I used real circuits in the lab, so it's not a model, it's real data, which causes some discrepancies from what we expect, but it is what's actually happening. And then for part 2, I did use the digital model, which makes the following assumptions: that resistance of wires is negligible, as well as ammeters, and that EMF is equal to the potential difference over capacitors plus resistors. So for part 1, the system is the circuit, surroundings are everything else. There's not really any relevant initial conditions, and then you can see the setup of the circuit visualized there. Use the node rule to predict that the currents throughout the circuit will be equivalent, and that the effective resistance is 147 ohms, and then we predicted that there would be 0.02 amperes of current, which was pretty close to the actual reading, 0.019, and when you flip the ammeter, that goes negative. Then you can see some more readings when we replace it with a voltmeter. These can be explained essentially by the fact that it's an open circuit, so there is no current flowing, and that the potential difference across the gap has to be equal to that across the power source. Then we continue to measure the potential difference across different locations, and we would expect over the entire loop to get a potential difference of 0. It was pretty close, it was 0.2, and then the current was still 0.02 as expected. The ammeter reading doesn't change because the voltmeter essentially allows no current to flow through it. Excuse me. Here you can see the graph of all the different potential differences. And then we're going to continue by adding an ammeter in parallel with the 100 ohm resistor. This essentially increases the current because it allows a path with less resistance for the current to flow through in comparison to the 100 ohm resistor. There are obvious flaws in the readings from the voltmeter, so these calculations are a little bit off. And then in part 2, we set up a battery, capacitor, and light bulb in series. You can see the setup there again. When we first connect the battery, the bulb starts out bright and then decreases until it goes out. This is because the capacitor is charging and the current decreases from the maximum to 0 amps. And then when we disconnect it, the same exact thing happens. It's just that the capacitor is discharging this time. And then you can see the times of charging down below. Here are some data that I collected in an Excel spreadsheet and then linearized to be able to find the RC value. And that's going to be correlated to the slope here. You're going to see the calculation on the next slide for the scenario with a 30 ohm light bulb. We tried measuring it, and we resulted with an RC value of 6 seconds based on some calculations. You can see how we manipulated the slope. What is expected is resistance times capacitance, which does end up being 6 seconds. Now time for discussion. In part 1, there are no discrepancies between the model and reality because it was reality. There was no model there. In part 2, certain components are treated as if they didn't have resistance. In reality, they would have some amount of resistance. The potential sources of error are essentially that the voltmeter and ammeter readings weren't perfect, so the data is slightly off, depending on what tools we were using. Excuse me. If we were doing the lab in real life, used an actual ammeter, we would get slightly different results because the ammeter does have some amount of resistance. If we used a real battery in this case, it would probably take a little bit longer for the capacitor to charge and discharge because the wires contain some amount of resistance. And for a final conclusion, there's a big difference between, not too big, but there's a significant difference significant difference between a simulated circuit and a real one. You can use capacitors as an almost pseudo timer to decrease current over time and eventually shut off a circuit over time. And then the node rule and the loop rule are very important tools when observing circuit behavior. Thank you for your time.